Hello. 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 Welcome everyone to the live stream. Sorry. Welcome everyone to the live stream. How's it going? Hope you had a good Tuesday. Hello everyone. Okay. So we are back live today again. What we're gonna do today is we're gonna continue with the algorithm R. And what are we doing today? We are solving some data structure algorithms problem from neetcode. Last time we left off, I think, 2 or 3 problems we did. And today, let's see, I'm planning to stream for 2 hours. So till 12:30 my time, it's 10:30 already. So after a long day of work and things like that, yeah, I think if we can complete up to 2 or 3 problems, it should be a good day. And it should be a productive day. So let's see. Okay, so without saying anything, let me quickly switch over to the live stream and then quickly get started. Meanwhile, say hello in the chat if you're watching me live. If you have any questions, feel free to drop in the chat. I'm happy to answer those to the best possible way I can. Okay, cool. And I hope the music is not too loud. Yeah, okay. So what are we doing today? We are solving some problems from neetcode roadmap. We already did the blind 75 things from here. So as you can see, I solved. Oh, I actually didn't solve all of them. So 3 or 4 is left, I believe. Yeah. Oh, 5 is left. Okay, so it shows right here. So 5 of the problems is left. But again, like, yeah, boom. Some of the problems are really a pain in the ass, but yeah, we'll try to solve those. But I don't want to go with the blind 75 anymore. I want to go with the roadmap, because like I mentioned, as you can see, if you complete a certain category, it actually gives you a pink thing. So again, the leetcode check marks is a dopamine hit. This right here is another dopamine hit, I would say. Okay, so the question is, what do we do? Well, one of the things I feel is we can do this. Stack. So you have stack, you have binary search, you have slide in window, then you have linked list, then you have freeze, words is left, backtracking, keep, graphs, one-dimensional DP, then you have greedy stuff, advanced graphs. Probably can do this together, two-dimensional DP, bit manipulation, and maths. Kind of hate a couple of those, but yeah, let's see which one is favored. So if it comes up with a very weird one, we are just gonna say, oh, we don't agree with that. No, dude, no, not advanced graphs. Okay, so let's do advanced graphs and let's see what exactly is in there. Okay, so I haven't solved any problem in advanced graph, and the main point here is that I don't know a lot of graph algorithms to solve this. So I have to do a lot of ChatGPT and Google, and I think it's a good learning thing. So even if I can do 2, I feel it's gonna be a good day. Specifically, I don't know Dijkstripe, primes, and cruscals, and topological sort of something which I know. But anyways, network delay time. Let's see if we can actually solve it. Given a network of n directed nodes, so I'm gonna put the volume a little low, at least for me. Okay. You're given a network of n directed nodes labeled 1 to n. You're also given times, a list of directed edges, where times is U is the source, V is the target, and then T is the time it takes for a signal to travel from source, and integer greater than or equal to 0. Okay. So you're also given an integer k representing the node that will send signal from. Okay. Return the minimum time it takes for all the nodes to receive the signal. If it is impossible for the nodes to receive the signal, return -1. Okay. So that's a very interesting question, right? So you have given 1 to n nodes and n nodes basically, and you number them from 1 to n, and you're given a weight with a certain graph, and you have to tell the minimum time it takes for all the n nodes to receive the signal. If it's impossible for the nodes to receive the signal, return -1. And then k is basically the starting node. So if I start at k, I have to see that how, like, first question is if I can travel the entire graph. If I can travel the entire graph, there has to be a minimum weight. If I cannot, then what exactly it is, right? So as an example, I can see right away that I can go from 1. From 1, I can go to 2, I can go to 4. So the minimum weight from 1 to 4 is 4. But then I can go to 2, from there I can go to 3, from there I can go to 4, which again is like 3. Total weight, so that would be the minimum. Yeah. So since I don't know any algorithm, I'll just try to figure out what we can do, right? How we can try and approach this problem. One of the things I feel here we can do is I feel we have to do a DFS. Okay. So let's actually get this particular thing done. So you have 1 which can go to 2, which can go to 3, which can go to 4, and then from here you can go I think the weight was 4, right? So from here, I feel what you can do is, if you do a DFS, you say I go to 1, from 1 I can go to 2, from 2 you have an option to go to 3, from 3 you have an option to go to 4. And what you can do is, so at 1 it would always be 0. It would always be 0. You also need to kind of keep a track that you have traveled the entire graph. If not, it doesn't make sense for you to actually do that, right? So from 1 you can go to 2. What is the minimum time? You have 1. From 2 you can go to 3. So 3, the minimum time you can reach by is 2, and then from 3 you can reach 4. So the 4 minimum time is 3. Right. Now you can also go back. It would unwind the stack and then it come back to 1, and then from 1 you would say, okay, let's go back to 4. So for every traversal you need to figure out where you stopped, kind of, right? Because I can come to 3 from some other node, but I just cannot say, okay, 3 has been visited. I can only say 3 has been visited while I traveled in this particular path, not the other way around. Not the other way around, right? So we have to somehow keep a track of where we came from 3. Yeah. So I feel like we can do a backtracking, because if, let's say that from 3 I came to 4, and then from 4 there was another path here, while I'm coming down this thing, I do not want to come back again, because do I want to come back again? Because everything is greater than 0, right? Everything is greater than 0, which means that it has to be positive accumulation. I do not want that. I want to minimize it. So I feel that if there's kind of a cycle, I really do not want to come back. I just want to move forward. Is what I think. There's also one more thing here, if I am not wrong, that is called Bellman-Ford algorithm. And this algorithm is like, I'm gonna actually learn this algorithm later on. First I'm gonna try to solve it my way, because this algorithm is something which basically, yeah, so William Faiset has this good video where it basically says that how you can travel from a given single source somewhere, shortest path between a single source vector to all the other vertices in a weighted graph. So that's what it is. Okay. Okay. So maybe that's the algorithm we have to go with, right? Maybe that's the algorithm we have to go with. Okay. Yeah. So now from 1 you can go to 4. So you haven't visited 4 in that particular way, and then it's 4. So the minimum still stays as 3. And from 4, I really probably don't want to go ahead anymore. Do I want to? Because I don't want to travel that path, right? I don't want to travel that path. Only one of them needs to be 0. What are the sources needs to be 0. I think that is how you can solve the problem. Let's actually do this. Let's see what ChatGPT has to say. Is the intuition correct? Very valid question. I think. And how is everybody doing? I hope my voice is clear. Close but not quite. Here's what off and what the right intention should be. There's a shortest path on a direct and non-negative weighted graph. The natural hammer is a Dijkstra's algorithm, or BFS, only if Ti equals 1. DFS with a Boolean visitor is unsafe. In weighted graphs, you might need to revisit a node if you discover a shorter path later. A Boolean visited would wrongly prune that. What you want instead is a best known time distance phi and only prune a path when the current time is greater than whatever it is. Okay. Don't initialize it to 0. 0 is a valid time, so use infinity or sentinel like big number. For voice, it's clear. Thank you. Thank you. It's better than before now. I think it's better than before, but with some changes, hopefully that's better. And hopefully the stream setup is also good. Yeah, I don't see any frame rates dropping lately, so good. This is the shortest path undirected, okay. Algorithm or BFS only if DFS with a Boolean visitor is unsafe in weighted graphs. Thanks. Thank you. Okay. Cool. Don't initialize with 0. 0 is a valid time travel time. It just can be 0. Okay. So use okay. For unreached. But then why can probably I have to use -1 because a distance can easily be but it probably has some sort of things in here. Oh, it doesn't say. What is the value of the maximum time that you have? It doesn't say, but I'm gonna consider it as a it's an integer array, so it can be maximum, so I don't think so integer max value would be a good thing to do. Instead I can simply say -1. Only 1 0 in the array is valid completion check. Other nodes can legibly end up 0. Okay, so that makes sense because for time can be 0, so that makes sense. You're not searching simple paths, you're maintaining best times. When with Dijkstra, you greedily expand the next node with the smallest current time, priority queue. Okay. So this is the shortest path problem on a directed non-negative weighted graph for which you have to work with the Dijkstra's algorithm. Okay. So I guess let's learn Dijkstra's algorithm. If it is a directed acyclic graph, which they don't actually say. Yeah, they don't actually say what exactly it is. So here, relaxing its outgoing agents and never need a backtracking visitor. If you use DFS, you must still prune via current time greater than this thing, return. That's essentially a DFS flavored Dijkstra, but it can revisit nodes and maybe slower. Dijkstra runs with a mean heap run in E log V. E is, I guess, number of edges, V is number of nodes, which fits typical constraints a naive DFS over paths can explode. Okay. So what is the correct intuition? Maintain a distance array initialized to infinity and a distance of k equals 0. Okay, so where do you start from? Repeatedly take the node with the smallest current distance and relax its outgoing edges. What does this mean? Only update a neighbor if you find a strictly smaller time. When done, if any node still returns infinity, okay, otherwise return the maximum distance. That makes sense. That makes sense. Okay. So I think the first thing we should be doing is, man, I cannot even spell it. KTRA. Dijkstra's algorithm. It's a greedy algorithm that finds the shortest path from a single starting node to all other nodes in a weighted graph with non-negative edge weights. Okay. It works iteratively selecting the unvisited node with the smallest known distance, making it as visited, and updating the distances of its neighbors if a shorter path is found. Do you have a diagram? I think they will have a diagram. Oh my god. Sorry for flashbanging. Okay. Sorry for the flashbang. Okay. It's called a single source shortest problem. So one of the questions I want to ask is why use Dijkstra not Bellman 4? What's the difference when to use what? Here's what I'm going. Okay. This guy's really sometimes. Awesome. Just now, I got to understand that my screen was not shared. Awesome. Oh shit, dude. Anyways, we are back live. The screen is shared now. The screen is shared now. Yeah. Oh, I have a single side around with that. Awesome. Okay, let's actually move through it. So here's an algorithm described by by Edgar Dijkstra, 1959, blah blah blah. Let's create an array D where for each vertex we store the current length of the shortest path from source to this thing. Initially, D of source is 0, and for all other vertices it's equal to infinity. In the implementation of a sufficiently large number, which is guaranteed to be greater than possible. Okay, so yeah, I get it. So you chose infinity because that's okay. In addition, we maintain a Boolean value which stores for each vertex whether it is marked or not. Initially, everything is done as false. The Dijkstra algorithm runs for n iterations. At each iteration, a vertex is chosen as unmarked vertex which has the least value D of V. Evidently, okay, which stores for each other. Initially, all vertices are marked false. Okay, evidently in the first iteration, the vertex S will be selected. Okay. The selected vertex V is marked. Next, for vertex, relaxations are performed. What does relaxations mean is the big question. All edges of the form V2 are considered, and for each vertex to the algorithm, and for each vertex 2, the algorithm tries to improve the value of D of 2. If the length of the current edge equals length, the code for relaxation is... I should understand. Okay. Finally, after n iterations, all vertices will be marked. So let's actually look at the implementation of how they're implementing. Okay, so you have const infinity, and you have a pair of vectors. I mean, vector of pair intent. Okay, so the question is what's the intent? Okay, but that's fine. Okay, so it's simply this. You have the adjacency graph dot size, then you say d assigned d is what? Okay, so everything is assigned to infinity, and p is what? I'm guessing p is a priority queue in here. I'm guessing p is a priority queue in here. That is what my best guess is. Okay. Okay, so then you say every one of them is false. That's fine. So you visited this thing. Okay, then you say source is 0, the distance of source is 0. So you always iterate over all of the nodes. V is -1 for int j equals 0, j less than this. Wait, what? What is this U now? Ah, okay. So if you have not visited that node and V is either equal to -1, which means it is not yet visited. I mean, don't have a... No, what is V? Oh, okay. Acha, the node you want to go to. Okay, I get it. So first you say I want to pick up any node, and then you say that whatever is the smallest node I can go to is something which I'll go. Okay. If, man, I hate these, like, I understand what competitive programming is, but look at this piece of code. How on fucking earth you're supposed to know what is S, what is D, what is P, and what is this weird thing where you have put a space between your like reference operator. What is this? I'm sorry. I mean, this website is really good, and but it's a giant pain in the ass to even figure out what on earth you have written. What is D? What is this? I just cannot understand. And okay, so one quick thing I'm gonna do in here is that is fine. So why can't it, if I'm not wrong, it was always FT, right? So this is distance, P is priority queue, and then you also have U, which is simply visited. I think that's a little bit better to read, honestly. Right, it's a little better to read. Now I can understand exactly what is happening. That is fine. Okay, so this is this, and you can simply say just and see graph. It's fine. Okay, cool. Quickly gonna just see one thing here. So you're saying everything is not visited, none of them are visited. So if it is not visited, and like the node, you have not picked up a node, or the distance of j is less than the distance of v equals, okay. So if after picking everything up, if you still say that, okay, if it's infinity, you break because you don't want to go down that path. Holy shit, what? That's called true. Okay, it's true. Okay, then you, what is this called? I don't know why it doesn't oh, okay, but this is edge. Second, okay. So distance visited equals true, so you visited that particular node, and for every edge, the bigger question here is, how are you even using the priority queue? I'm not even sure how you're using priority queue. The only place you use is here, and you assign every one of them to -1, and you're saying this 2 is to v. Yeah. What is this? ACM is doing online judging. Okay, I'm not gonna go see there. I'll try to find meanwhile, let's see. Greedy, always pick the next node with the smallest current distance. No, only with non-negative nodes, weights. With priority queue, you have e log v, when to use when all the edges have greater than 0, and you need the shortest path from one source efficiently. Bellman-Ford is dynamic programming, and that is greedy. Okay, so relaxes all edges up to v minus 1 times. Yes. Okay, so this is v into v. When some edges have negative weights, or you need to detect negative cycles. Okay. The graph is dense, so you're not sure about this thing. Okay. So I still didn't learn anything about Dijkstra's algorithm after reading everything, right? So we gotta find a good article. I don't know if I watch this now. I'm not gonna watch it if there's gonna be copyright strike and things like that. I don't want to go through that. But it's a directed graph, right? So I just cannot simply say where I'm gonna go because it needs to have an edge. Right, it needs to have an edge, otherwise I would end up doing stupid stuff. We use a min heap as we need to find the minimum time. We create an adjacency list for the given times. The weighted edges. We also initialize an array of size n. Number of nodes, which represents the distance from source to all nodes, initialized with infinity. What? If the unvisited set is empty or contains only nodes with infinite distance which are not reachable, then the algorithm terminates by skipping to step 6. Okay. If the only concern is a path to a target node, the algorithm terminates once the current node is target node, otherwise the algorithm continues. Okay. For the current node, consider all of its unvisited neighbors and update their distances to the current node. Compare the newly calculated distance. Compare the newly calculated distance to the one currently assigned to neighbor and assign a smaller one to it. For example, if the current node A is marked with a distance of 6 and the edge connecting with its neighbor has length 2, then the distance to B through A is 6 plus 2, 8. If B was previously marked with a distance greater than 8, then update it to 8. Otherwise, keep its current distance. The path through to B is not the shortest. Okay. After considering all of current nodes and visited neighbors, the current node the current node is removed from the unvisited set. Okay. So for every vertex in the graph, you say distance is infinity. Previous is undefined. I don't know what that is. Okay, so maybe like previous where you're coming from. Add V to the queue. Okay. While queue is not empty, vertex in queue with minimum distance is U. Wait, what? Vertex. Okay, so first you return out the source and after that you go for everything. So whatever is the minimum distance of your neighbors, you pull that out. Okay. And then it doesn't quite say what Q is in here. S is empty sequence, U is target. So you added all the nodes in the queue with infinity. With vertex priority, what does that mean? So what priority are you going to store with? Okay. While queue is not empty, you extract the minimum and you get something out. And for each and every edge for U to V, cannot understand, man. Like, that's why I hate these things. Like, why can't you simply use proper terminologies? Why do you have to fucking say U, X, Y, Z? That's not how you write a code, and that is not how you're supposed to write a pseudocode. Because not everybody can be as smart, or not everybody can, you know, always follow along. It just doesn't happen with every mental model. So that is pure gatekeeping. Q.add with priority. For what priority? You can simply just write a sentence saying that, hey, this is a priority you need to. Okay. Let's first learn Dijkstra's law step by step. Exactly. Relaxation. For every edge with time W, if distance plus the W is less than distance of current plus whatever I'm adding to go to you is less than what you already are if you have reached from somewhere else, then update the distance v and push this thing to the priority. Okay, so when a node u is popped from pq, its distance is finalized. Can get better than non-negative with non-negative edges. So okay, so when something is popped, that's what the answer is for that particular node. After pq is empty, okay. So distance, we start with 1. Well, actually it's 1 index, but yeah, that's fine, I guess. So iteration, so you push 0 1 into the queue. Why 0 1? Distance 0 1 is a node. Okay, then you relax. What does relax means? You want to explore your neighbors and see what's the next shortest path that you want to go to. It's as simple as that, I feel. And it's not just the shortest wait. I want to check that, like, whatever distance I traveled to reach here, plus whatever distance I have to travel to reach at the next node, it has to be, that total distance has to be less than whatever distance I'm presuming it was required to reach that node first, the second node, right? And once you reach that particular node, like I would say that which is the lowest one, I would pick that guy. So if I haven't visited anything, so that is one of the options. But if I have visited, I want to have to take the minimum one. That's pretty much it. Okay. So let's actually do a dry run with this thing of, you know. Okay, let's actually do a quick dry run on these things. So here you have 1, where you can go to 2 at a distance at a weight of 1. From 2 you can go to 3 at a weight of 1. From here you can go to 4 at a weight of 8. That's weird. So it's UVTI, okay? So from 1 to 2 you went this, from 2 to 3 you went this, from 1 to 4 you went with weight 4, and 3 to 4 you went with a weight 1. That's pretty much your graph, right? The next thing that you want to do is you want to do a Dijkstra where k is 1. The very first thing about Dijkstras is that you have a single source and you want to find the shortest path of reaching every single node with non-negative edges, is when you would work with Dijkstra. And it's more of a greedy algorithm saying, okay, let's just say I'm at a current node. Whatever next node is with the shortest path, I'm going to go there. So you could have arrived at a certain node from different other places, but from the current node, can I reach that node with the shortest path? If yes, I'm going to do that. Okay. So what you have to do here is that, let's say 1, 2, 3, 4. So every one of them is infinity. Instead of infinity, let's just say -1, -1, -1, -1, -1, and everything is visited false. Okay, that's basically it. Now in here you come and say that it's 1. So let's just consider 1 based array. So this is 1, so this is now 0 because it's there, and you make this as true. Okay, you do that, and after that in your min heap, because we have to find the minimum distance, you say 1, 0. This is what you push in your heap. If you pull out anything from the heap, it has to be the final one. So like it's basically done for. Yeah. So the current node is 1 and the distance is 0. So now what all neighbors do you have from 1? If you do a BFS, the neighbors you have is 2 and 4. So the neighbors you have is 2 and 4. So if I go to 2, it is 0 plus 1, and this is 0 plus 4. If you look at this particular thing in here, you would say that if you look here, so if it's either -1 or it's greater or greater, you would simply say that, hey, this is less, right? This is less, so I would pick 2. So you pop this guy out and you say 2, and distance would become 0 plus 1. So here you can simply say 1, and you can push this in the heap. Push this in the heap. Question is, do I want to push, because if it's a BFS, do I want to push everything to the heap? It's a good question, but I don't know the answer right away. But let's see. Sorry for that. Okay. A stream going good. Okay, stream is going good, I suppose. Okay, so now in here, if you have 2, from 2 you can only go to 1, this one. And also I have visited this. So from 3 you're saying, okay, I visited this. My question here is, when is a time when you would have multiple things like this, right? So you can have something like this, where you say it's 1 2 1 2 3 1. Okay, let's try and learn Dijkstra with this particular example in here. Okay, so you have 1 and 2. Have 1 2 3. So from 1 to 2 you can go with the distance of 1 or weight of 1. From 2 to 3 you can go for distance of 2, sorry, 1, and you start with 2. So 1 2 3. So this is false, 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 -1 -1 -1, right? So what you do here is, the first thing you do is k is 2, so you say this is 0 and this is true, and you push this in the heap. Once you push this in the heap, you gotta say, sorry, you pop this out and you say, okay, where all I can go? I can only go to 3 in here from 2. So you say, okay, let me go to 3, because that's the only option. But also we have to check that your current distance, which is 0, plus the next distance, which is 1, should be less than equal to this thing, distance of 3. Or distance of 3 is -1, which means we never actually visited it, right? So once we do that, sorry. So once we do that, we can simply say, let's actually go ahead and yeah, I think we can simply say, let's actually go ahead and like visit 3, where you would say 3 of 1. Then you would pop it out, and 1 is the distance that you put here, and this has to be true. And can you go anywhere from here? No. So if you go around, you would see that there is one guy with -1, which means that you cannot visit every other node, so it becomes -1. So Hmm. What else is it? Distance. We have to talk about visiting. True, false, false, false. Now, pop 1 0. Mark 1 as iterate over its neighbors 2 and 4. So for 2, 0 plus 2, distance is -1. So we can choose 0 plus 2. And for 4, distance of 4 is -1. And we can choose 0 plus 4, so 4. Since 2 is less, we decide to push 2 1 in the queue. Once we pop this 2 1, mark it visited and update the distance. Sorry. Mark it visited and update the distance 1 and iterate over the process till queue is empty. So we never visited 1 to 4 ever, and at all times only one element will be present in the queue. Is that so? Is that so? Oh. Okay. Okay, yeah, that is exactly what I was talking about. Okay, so Dijkstra's algorithm seems pretty simple, right? Let's quickly get on to do with this, and what we want to do here is sync code. Okay, so once this is done, I would also want to okay. So what did we do in Dijkstra's algorithm? First thing first, we have to generate this adjacency list, right? Private list of integer generate graph is int n int times, right? So, and also this is this, and I think we need to zoom this a little bit. That is probably too big, or is it? Okay. Is Omar keyword the height? What the heck is an Omar key? Oh, DHH is Ruby of Rails developer, or founder, or creator. Ruby on Rails. Ruby on Rails. Okay, cool, pretty cool. I created a ton of fresh RS installation. Is fully configurable, beautiful, and modern. This thing. Okay. Can you show me some? Oh wow, with typeline and stuff like that. Looks pretty cool, huh? Can you go fast? Not fast enough. Holy shit. Those animations are sick, I love it. That's pretty sick, huh? A lot of people are running over market. Wow, okay. So it is Arch with some beefed up stuff? Is that what you're talking? Okay, anyways. Definitely not for us right now. Definitely not for us. Okay, so how do we do this, right? How do we do this? We need to say because we need to preserve the distance, right? Wait a second. If this is the input, how you're taking the input like this? The fuck? Oh, it's just taking the input like this. Do you have anything else? CP? It's vector of int. Okay. JavaScript. Oh, I know, because you're doing this. Okay, cool. Times, right? So what I do want to do here is that so let's do this for int I equals 0. This is this. I just want to do that. So now I can simply do graph.get. So int u. So let's call it source -1, and destination is this, and weight is this. So you first get of the source dot add new pair of this. That's pretty much it, and you return the graph. So zooming a little bit more, just let me know if this is okay. you guys can see what I'm doing. The next thing I do want to do here is that I want to say that can I okay, what do we do then? Where is this guy? Yeah, so we generated the graph, and then we have to generate these kind of bookkeeping stuff in here. So I'm gonna say boolean visited is this, and then this here is distance, not distance, delays, I'm gonna call it. Okay, arrays.fill -1. Okay, then I also need a priority queue of length. I don't have to give the length. I don't have to give the length. I can simply say a comparator comparing integer pair of weight. Oh, edge dot then comparing, because there can be a then comparing vertex. This is not required, but in case there is a conflict, I would like to resolve it. I mean, it's automatically going to resolve it, right? So whichever is just going to say, oh, we cannot compare it, so it's equal. So I'm just going to leave it at this. Okay. So now, first thing first, visited. So I'm not going to say visited right away. I'm going to say delays of a -1 is equal to 0. PQ offer this thing, while PQ dot poll. Okay. So now I can simply say pair dot edge visited is true. So now I'm gonna go over the neighbors that I have. So I'm gonna say generate graph n times. So I'm just gonna say graph.get this thing .for pair. I'm gonna say in current delay should be the edge, and this is vertex, my bad. Yeah. If delays visited of e dot vertex, if it is not, and or p dot delays of p dot vertex not equal to -1, equal to -1, or current delay plus p dot edge is less than p dot vertex, Okay. And I'm gonna say this. For int delays are return -1. Okay. Awesome. Awesome. But in here we already did -1. Fascinating. So since it's a record, Okay, that's wrong. That's right. Okay, so now we are still talking. Okay. Hmm. Hmm. Maybe. Question is, why do we need this? Hmm. Mm-hmm. So let's actually solve some extra problem. Sorry. I actually did the extract here. I didn't know. Okay. Mm. Given 2D array move time. Okay. represents the minimum time in seconds after which the room opens and move to. मतलब so you're here and this room will open after 4 seconds. So after 4 seconds, when you're at 4, it opens and you have two different options in here, this and this. So you can go here or you can go here. Which one do you go to? The distance is the same, but I'm not getting this 4-4. Acha, this is 0, this is 4, this is 4, this is 4. So after 4 seconds, both the rooms open. So I can probably go to either of these. So I'll go to both actually and try and explore. And this is also open and you come from here to here. And the minimum distance is like for this is. Okay, I get it. So at that particular second, this room opens. At that particular second, this room's open. So you have to wait till you can move to a certain, you know. And here you can only move horizontally or vertically, but we have to somehow keep a track of where we visited because I don't want to go to, we don't want to go to a certain. Okay. True. Your polis, of course. After your polis, it's 1001. It's correct. After that, kind of is saying, yeah.
So if it is this thing, what I'm simply gonna say here is I'm simply gonna say current time plus move time to next row next column plus 1 should be the time taken next column. And yes, that's what we have to do. And we can remove total time. We can just simply return times of -1. This one, of course, that will not work, but we can say this for our case. Solution. How come? The fuck? So if next row is yeah, but I want to go for the next direction. I don't want to stay in that direction, so that's why I say did something stupid. I feel like I did something stupid. Okay, this is for everything. That's a good question. No, so the first one fails. Okay, so we did something damn stupid. Okay. Okay. This is what I don't understand. One 0 minus 1 0 0 1 0 minus 1, and you say that okay, take the direction. The next row would be row plus direction of 0. Next column would be column plus direction of 1. That's correct. If the next row is not within the bounds, where next row is less than 0 or next row is greater than, dumb mistake. Okay, so this is correct. Where it's wrong, I feel don't have to add that. And at the very end, no. Just be quickly back. Yeah. Okay, I think I'm gonna stop streaming right away. I'm gonna take this offline and I'm gonna solve this offline. The reason why I'm stopping streaming right now is already 12:30. I didn't notice, and yeah, I have to get sleep and tomorrow this office again. So tomorrow, hopefully, I'll come online in the evening.
I'll try to come early, but the problem is, like with every other work, things don't pan out, and it doesn't quite happen according to plan. So let's see. Let's see if I have, if I can, I would actually do that and come early. If not, we'll see. But yeah, thank you so much for everyone who tuned in. Thank you so much. I would say it's a good. I would say it was a good session because of the fact that I actually learned Dijkstra. I never really learned Dijkstra, and the first time I actually learned Dijkstra. So I would say it's a very good session, and yeah, we'll continue with advanced graphs till we actually solve all of the neetcode problems. And as and when we actually learn some algorithm, what we would do is we'll come to leetcode, we'll filter out with those tags, and then we'll try and solve a couple more problems to get used to that algorithm. This is what my plan is, so let's see how it goes. Okay, thank you so much, and bye bye, have a good night.